Hi everyone, I'm Jonathan or Teddy McManus. I'm in my first year of my PhD at Liverpool with supervisors from the CCDC, Angelis Pulido and Jason Cole. I'm from Liverpool, Andy Cooper and Vitaly Kalin, who's my primary supervisor. I'm going to talk about, very generically, comparing different crystals. So this is more about geometric invariants of crystals more specifically. So a couple of prerequisite definitions. We use the representation of crystals with a periodic point set. So with a unit cell and a motif, a set of points within that unit cell that hopefully is reasonably widely used. So in this case, we say a point set because we're actually representing each atomic center with a zero-sized point. The unit cell is a parallelepiped represented with 3 lengths, 3 angles, in this case a cuboid. And the motif M is the set of points that reside within that unit cell, that parallelepiped. And I'm using S to represent the infinite set of points generated by tiling the 3-dimensional space with that unit cell and point set. So what's the problem with defining crystals this way? Unfortunately, there are just too many choices. There's an infinite set of possibilities for unit cells that are viable for a particular crystal. And even given you've chosen a unit cell, there's an infinite set of possible motif point sets that can all represent the same crystal. And I have a little example here with different unit cells plausible in 2 dimensions, and then translations, rotations of the whole space, all sorts of different things that would all represent the same crystal, the same rigid crystal. So how are we going to tackle this? The first explanation is about defining an isometry as a rigid motion. So in this case, it's the translation or rotation and/or rotation and/or reflection if need be. So what we're saying is if we have a representation of a crystal and then we translate, rotate, reflect, we want to know that we're still talking about the same crystal. Those 2 representations are equivalent up to isometry. So we're looking for an invariant or some form of barcode that will represent those 2 equivalent representations as the same. So this is where we bring in the invariants. So the first property we want from an invariant is that it is invariant under isometry. So this is, as previously said, if we throw in a crystal representation, a unit cell and motif, and we'll get a barcode out at the end. If we rotate, translate that and throw that in, we want the same barcode. We don't want it to change when we perform a rigid motion. So what that means is if we throw it in, we get the same barcode. That doesn't necessarily mean that if we put 2 crystals in and get the same barcode out, they are the same crystal. For that to be the case, we need the property of completeness. So this means if we throw in 2 representations and we get the same barcode, we know that those 2 representations are of exactly the same crystal structure. Now, a sub-property of completeness is reconstructibility. So once we know that any one barcode represents a specific crystal, it's incredibly valuable for us to take the barcode and be able to reconstruct the entire crystal from that barcode. And the final property that we're looking for is continuousness. So this is quite a difficult property. And the idea is that if you perturb atoms or if you slightly skew the unit cell, you will end up with a barcode that only slightly varies as well. And the combination of all of these properties can be incredibly powerful. We can, for example, take a potential crystal, look all around it in the space and find things like how stable it is based on the energy barrier, lattice energy of crystals around it, things like that. It's very, very powerful. So I'm going to next talk about a specific invariant, and Dan will also talk about an invariant with different properties, different potential values. So I'm going to start talking about the isoset invariant. So the first thing to know about is our definition of a local cluster. So this is very similar to an atomic neighborhood. We've got a center atom or point in this case, and here this diagram is the unit cell of a square with these 5 points in the motif. And we say, okay, we pick a center atom, we pick a radius, and it's all of the atoms that are within that distance. Just this little formula here. And if we move on and we think, okay, ordinarily we might fix this radius and compare atoms within it, but we're actually going to treat this radius alpha a little bit more fluidly. And if we compare different atoms' neighborhoods at a specific radius, we want to look at what happens as the radius that we choose increases. How do those neighborhoods compare to each other? So the first factor is if this radius is incredibly small, smaller than the minimum distance between points, then the neighborhood will only consist of 1 point. And we could say that all points are identical. If we're just looking at the neighborhood with a radius that small. So in this case, if we have a very small radius around a point, 1 point in the local cluster. But what happens when we increase that radius? And so what we then define here is this alpha equivalence. So alpha is the radius here, and as alpha increases, we define two atoms as alpha equivalent if the neighborhood, the local neighborhood at that radius alpha, can map onto each other with a rigid motion. So for example, if we look at the neighborhood around this point and this point, if we rotate that by 180 degrees or reflect it, we can map the local cluster onto the other local cluster. So at that radius, they are alpha equivalent. And alpha partition is very simply just splitting up the motif points into a set of alpha equivalent classes. And now we're going to demonstrate a little tree here. So this is a one-dimensional example. And we're looking at what happens to the partition, these alpha equivalent classes, as alpha increases. So we have alpha as 0, very, very small. Every neighborhood is just the point on its own. And so they're all equivalent. And this represents the equivalence classes here. There's just the one equivalence class. They're all equivalent. As alpha increases to 1, every point in this, and we can think of this as a unit cell, every point has 1 and exactly 1 point within 1 distance here. So this atomic neighborhood is just these 2 points, and we can reflect it, but they're all equivalent. So there's still only 1 equivalence class. And we increase to 2, and this is where it gets a little bit more interesting. The equivalence class actually splits, and the partition has 2 equivalence classes. And so that increases, and we split these into 2 because there's 2 within the neighborhood here and 3 within the neighborhood. And these can be mapped onto each other by a reflection. So they're within the same equivalence class. And the interesting thing here is that as alpha increases even further, we still get the same number of equivalence classes. The partition doesn't change. And also slightly relevant, the symmetry group of the neighborhood doesn't change either. So what that means, there is actually a point for any representation where the equivalence classes don't change anymore. And that is a stable radius. We call that a stable radius. So we prove the existence of such a stable radius. And if we find the collection of equivalence classes at that stable radius and collect the local clusters, the atomic neighborhoods for each of the points at that stable radius, we get a solid representation of that crystal. And if we want to compare 2 crystals, we simply take the largest stable radius and compare the 2. We've got ways of comparing 2 crystals that way. So we end up with, this is actually a continuous, complete, reconstructable invariant for crystals. So I've pushed through a little bit there, and oh, I forgot to mention, yes, the ISO set is specifically the set of alpha equivalent classes at the stable radius. Thank you for listening, and I'll stop sharing.
So since the motivation for continuous isometry invariants kind of been laid out already in the last 10 minutes, I only have 1 slide on it, but it means that the first slide isn't straight away a definition, which is kind of messy. So this is what we're trying to resolve. The top two are the same set, and obviously if you fell for the trick, you probably that's probably fair, because I've done something quite evil and translated these 2 points towards the corner. One popped over the edge, and now it looks completely different from cell and motif perspective. But obviously, because you can get one from the other via an isometry, they're literally the same thing. And this one at the bottom here is only slightly different from either of them. What I did was I took this and extended the unit cell, and then perturbed one out of the 4 points in the motif. So now the symmetry is broken. I can't reduce the cell to a cubic anymore, but it's still similar to these two sets. We only got it through a small perturbation. So whatever we make should be able to identify these top two as exactly the same and identify them both as similar to this bottom one. So we only have one slide to define the invariant. It's relatively simple to construct, and then we'll have results. So to construct the average minimum distance, which is the invariant, which looks like this, it's just a vector of numbers. We'll start by constructing this bigger matrix. So I've got an example with 3 motif points here. And that means we're going to have 3 rows in the matrix. So there's 1 row for each motif point. And we choose some number k, which can be any natural number, to have as many columns as. So that can be any number you choose. And how you construct this matrix is pick on any motif point. I've picked on this one. We measure the distances to its first k nearest neighbors. So we've got 0.452 and then 0.536. And we just put these distances in order into one of the columns of the matrix. So we get a row of a length 5 increasing sequence. Then do that for every motif point, and we get 3 rows. Pretty simple. This is a good idea because if you want a continuous isometry invariant, isometry means doesn't change interatomic distances, and continuity is pretty much gifted to you for free if you use interatomic distances, because if I smoothly perturb a point, the distances between points smoothly change as well. But the issue is that this matrix, first of all, the order of the rows depends on the order I chose for my motif points, which is bad. But also, if I was to extend this unit cell to include 6 points instead of 3, all of a sudden my matrix up here hasn't got 3 rows anymore, it's got 6. And the easiest way to resolve that is just to average over the columns to get one vector. So that's how you form the average minimum distance for 1k. If I increase k, then none of the previous values change as well, which is nice. Very briefly, there's another way to remove these two issues, which results in a stronger invariant, but I'm not going to elaborate on that. It might be relevant later. So this is the whole definition. And we're just going to quickly run through the properties of it to show that it kind of ticks boxes we might want it to tick. So first of all, there are isometry invariants, and they're continuous, which is, I mean, it'd be pretty bad if it wasn't, since we set up the motivation as such. Unfortunately, with regards to completeness, we think they're not complete. It's actually relatively difficult to confidently decide that one way or the other, but we're pretty sure they're not complete. Not that it necessarily matters, because you can have continuous isometry invariants that are not complete, but very useful, like density, for example. We're going to see in a sec how AMDs might differ from the answer that density measure gives you. And lastly, but probably not least, is that they're super fast. They're just a vector of numbers. So calculate it for a structure once, and you can just keep it and compare with it as many times as you want. And we compare using the simple L infinity metric, which is just the maximum deviation between two of these vectors along any dimension. So it only takes a few minutes to do thousands of structures, and once you have their AMDs, it only takes a few nanoseconds to compare. This is nanoseconds, by the way, not milliseconds. So, you know, it only takes a few seconds to compare thousands and thousands of structures. And the toy set that we're going to use to see what it can do is T2. So we have about 6,000, give or take, simulated structures from a CSP output. And out of the 6,000, 5 unique polymorphs were actually synthesized. So How we're going to test our invariant is by asking it what it thinks are structurally similar things to these guys, if it can pick them out. And since it's fast enough, we're going to be able to do this for the whole data set. But before that, let's look at one example with regards to density, where I've picked 3 structures from T2 simulated, 2 of which are obviously the same thing, although they differ just a little bit in density because they're not literally identical. And I've picked some other structure here, which is not related to either of them in terms of actual structure, but just so happens to have a very, very similar density to this. And this is just what happens because density is a single value measure. It only takes on a reasonable range of values. So if you have a big data set of 6,000, you're bound to have 2 that overlap that aren't related. And you can see that in the density differences in the triangle. But in comparison, the AMD comparison gives you a much more reasonable answer, if you like, in terms of what we care about, relatively speaking. But instead of looking at single examples, we want to see what it can tell us about the whole data set of T2, because it's fast enough to do so. That's pretty much its advantage. And we're going to do that using a minimum spanning tree. So to briefly recap, or if anyone has never heard of a minimum spanning tree, if you take any graph with weights on the edges, then you can create a minimum spanning tree by choosing a subset of the edges where there are no cycles in your subset, such that all the nodes are connected by some path, and such that the tree you chose has the minimum total weight on all the edges. So the idea is that the minimum spanning tree is going to have relatively low cost weights on all these edges. And we're going to do this, how we're going to do this is have each node be a structure in T2, and each edge has a weight equal to the metric provided by our invariant. So hopefully, when we plot T2 as a minimum spanning tree, the similar things cluster together and the different things are apart. And we use this package called tmap to do this. You can go here if you want to find it yourself. It's good for plotting interactive maps like this. So this is what T2 looks like when we plot as a minimum spanning tree using the invariants. The red dots are the actual experimental structures which have appeared on these different places in the tree, and the colors are representing lattice energy. So yellow is high energy, and you can see the experimental structures live in these little low energy pockets, which makes sense. But it's more nuanced than that. If you look inside these circles, which aren't arbitrarily drawn, by the way, they're specifically there for a reason. Inside these circles are nodes which pretty much look virtually indistinguishable from this structure. So our invariants are trying to tell us that these are very similar things, and it, generally speaking, gives the right answer. These numbers by the names of the structures, by the way, say times 8 or times 11, is the number of matches it found. And I declared a match as packing similarity, giving you basically an exact match. So in this case, we've managed to place our experimental structures next to their nearest neighbors out of all of T2. And this didn't take particularly long to produce. And AMDs and the other invariant as well, I guess, are fast enough such that you don't have to stop at, say, 6,000 structures. We can feed through many more. I've got one more example of a minimum spanning tree on something else. So here, the color is by ref code. So take glycine, for example. There are like 50 structures in the CSD, all with ref code glycine, and they all got the same color. So what you're seeing when you see a branch all the same color is one family, one ref code, which have all been clumped together because presumably they're the same polymorph. And you get all sorts of interesting little arms where the families have been automatically clustered. And you also get interesting little areas like this. I've just highlighted one where different but related structures appear together. These are all very obviously related. If you were to look in the CSD, they're all sort of very distinct long chain hydrocarbon crystals. And this thing's obviously huge, so you could explore it forever, but it's more of a proof of concept that the new invariants are fast enough to get you results for enormous or at least very large sets of structures, but also fine enough to group and separate based on structural detail rather than it's a metric that's a little too simple to do something like that, like density. So initial results have been interesting, but that's my last slide. So I'll stop there. If there are any questions, I'm happy to answer them.